Hello, class. Welcome to a short lecture on graphs. So in this lecture, we will cover some basic graphs for categorical data. And if you recall, categorical data is typically what we call non-numerical data or nominal or ordinal. Then we'll discuss some graphs for numerical data. Typically, this is what we consider to be interval or ratio data. Then we'll talk about some misleading graphs, specifically how you can mislead the reader without actually lying by manipulating certain things on the y-axis, sometimes called the ordinate, and how we can mislead the reader by manipulating certain aspects of the abscissa, sometimes called the x-axis. And then, as always, we'll do a few practice questions. So what are the most common graphs for categorical data? You have nominal or ordinal data. We've got the bar. We've got the Pareto. This is actually named after, I believe, an Italian mathematician, Alfredo Pareto. You may have heard of the 80-20 law. This is the same gentleman. And then a pie chart or pie graphs. These are the three most commonly used graphs, charts, if you have categorical data, nominal or ordinal. So here's an example of a bar graph. Right? And in this case, we have on the x-axis letter grades. We know letter grades are ordinal in nature. And we have, since they're ordinal, they're in a particular order. The width of the bar is irrelevant because the width of the bar is not constituting an interval, which will be important when we get to numerical types of graphs. But they do need to be the same. You could attach them, make them closer if you wanted. There's no hard and fast rule on that. Typically, you will see frequency on the y-axis, but you could have relative frequency, you could have relative percent, you could have percent. So this is what you would typically see, frequency or percent, but it could be any of the others that we mentioned, especially in the other graph where we did frequency distribution tables. Here's another example of a bar graph, but in this case, it's a compound, meaning we've got two variables. So we've got letter grade, and then in addition to letter grade, we've got sex, male or female. Here's an example of a Pareto. Pareto looks a lot like the bar. So we still have categorical data, typically on the x-axis, but we've done two specific things that make it different than the bar. So it does use bars. The first thing that's different is you must arrange your variable, the various subcategories, from highest frequency or highest percent or highest relative frequency to lowest. And if there's a tie, there's no universal rule that says one has to come before the other, but you arrange them from highest frequency to lowest frequency. The second thing that you will see is this looks like a little fishing pole, a rod over the data. This tells us the cumulative frequency or cumulative percent. In this case, it's telling us cumulative percent. So we know the C's constitute, in this case, 40% of our grades. And we know that since we had 10 scores, 4 out of 10 times 100 is 40%. C's and B's collectively are going to have 60% of our scores. And then when we have C, B's, and D's, we come up and we'll see that's 80% of our scores. And then 90% of our scores. And then 100% of our scores. So it does two things in addition to the bar. You have to put them in descending order from highest frequency or highest percent to the lowest. And then you typically have this cumulative percent bar that goes on top. And then finally, everybody's favorite, the pie chart. In this case, I have percent. Sometimes you could have frequency. You can actually have both if you wish. In this case, it's color-coded. There's no rule that says the largest slice of the pie has to go on the bottom. It could go anywhere. The point is, visually, The slice of the pie corresponds to the percent that you have. So this orange represents 40% of the pie. This represents 20%, and so forth. Pie charts are useful. They're easy to understand. I probably actually violated somebody's rule by giving me this 3D perspective, which probably exaggerates how big this is. But this is an example of a pie. You can see it has a downside. It's useful when we have small categories. So in this case, we only have 5 categories. If we had 15 or 20 categories, some of the pies or slices of the pie might be so small as to be uninterpretable. You couldn't actually see the frequency or the percent. And so when you have just a few categories, I think pies are a useful categorical type of graph, but they start running problems when you have multiple categories. Some common graphs for numerical data. Histogram, the frequency polygon, and these two tell you the same thing, just with a slightly different setup. I got the stem and leaf, the box and whisker, sometimes just called a box plot, time series, and a scatter plot. Time series and scatter plot are a little different because by their very nature, they have to be bivariate in nature. They're not like the other graphs that we've shown. So this is a histogram. It looks a lot like a bar. In fact, it uses bars. The primary difference is that the bars typically represent an interval. And so the width of the bar actually means something. So this width, this interval, contains all the scores from 50 to 59. This one, all the scores from 60 to 69, and so forth. Sometimes you will see the histogram where there is no space between each of these categories intervals. Sometimes the author will do that to let you know it's discrete data. If you have continuous data, sometimes they will just keep the bars, push them all together so there is no space between each interval. Like the bar, we could have frequency, we could have percent, we could have relative frequency. Doesn't change the shape. The shape remains the same. Just depends on what type of information you wish to provide along your y-axis or your ordinate. This is a frequency polygon, and you can see they look very similar in terms of shape. The difference is, whereas we're using intervals with the histogram, the frequency polygon is going to use a midpoint. So it's going to take this midpoint, this midpoint, this midpoint, this midpoint, and this midpoint, and collect them or connect them with a line. And then to close it out, because a polygon is a closed-sided figure, it will just go down one interval, which has a frequency of 0, and it will go up one interval, which has a frequency of 0. And so you get this closed-sided figure. Some people prefer histograms. Some people prefer polygons. They tell you the same information, just in a slightly different format. Stem and leaf is one of my favorites. The reason I like a stem and leaf is the only graph where you can actually see the shape of the data using the actual data. So if you look at this, you can't tell me what the underlying original data was simply by looking at the graph. And same with this one. You can't tell me how many 50s or 51s or 52s there were in the data set simply by looking at the histogram. But if we flip the histogram on its side, you'll see it looks a lot like this shape. But in this case, I have a stem, and the stem size is 10. So this lets me know this is 50, 60, 70, 80, and 90. And I have a 59. I have a 65 and a 67. I have a 71, and I can see here is my mode. I've got two 72s and a 76, an 84, an 87, and a 94. So with the stem and leaf, you can actually recreate the actual data from the graph itself because it uses the actual data. The downside with the stem and leaf is it's limited to the amount of data that it can handle. So it can easily handle these 10 scores or so. Could easily handle maybe, up to 100. I see a lot of books that say anything more than 100, it starts to get too busy. Uh, but if you try to recreate a stem and leaf with thousands of pieces of data, I think the graph would get so small that you couldn't actually see the underlying data. And so you might as well just try another type of graph. Um, so as a rule of thumb, they're useful up to around about 100 pieces of data. After that, they may become difficult to actually see the underlying data, because in order to fit it on the page, you have to make the underlying data so small that it may not be legible. Okay? So again, we got a stem and a leaf. We got a 59, a 65, a 67. I can quickly point out the category with the highest frequency, and I can also quickly find my mode, 60 or 72, and another 72. If you had a interval where there were no scores in there, you wouldn't leave it, omit it, you would still keep it. You would just have 60, and then there would be nothing here. Here's a box and whisker plot, sometimes just called a box plot. This is a little bit different because instead of giving you the typical 5-number summary, this one actually gives you a 6-number summary. But the traditional 5-number summary that you get with a box, here's my box, which is the interquartile range, the middle 50% of my data. And these are my whiskers. And so the 5-number summary that I get is I get my lowest value, which looks like it would be a 55. Occasionally, if there's an outlier, they might put a little asterisk right here or a little star to let you know there's extreme values. But in this case, there weren't any outliers. This represents the minimum value. This represents the maximum value, which would have been about a 98. This represents Q1, in other words, the 25th percentile. This represents the median, which is always Q2, which is the 50th percentile. And this represents Q3. So minimum, maximum, Q1, Q2, and Q3. And the distance from here to here, remember, is what we call the range. And the distance from here to here is what we call the interquartile range. It's the difference between Q3, or the 75th percentile, and Q1, which is the 25th percentile. In this particular box plot, we actually have a 6th piece of information, and that is the mean. But you won't always see the mean in a box and whisker plot or just a box plot. But in this case, Excel did generate the mean for me. Looking at this data, I would probably say it's a little bit positively skewed, because I can see this whisker is a little bit longer than this whisker. I can see the mean is slightly larger than the median, and I can see this quartile is larger than this quartile. Here's a scatter plot. We will talk more about the scatter plot when we talk about bivariate data, specifically the Pearson product, moment correlation coefficient, or just Pearson's R. But unlike the previous graphs, this graph always displays the relationship between two distinct variables, such as grades and IQ. Not the variable in its frequency, not the variable in percent, but the variable in a second variable. And so in this case, we can see we probably would end up with a nice positive correlation. We can get a visual representation of what the relationship between these two variables would look like. We could test for outliers. We can look for that linear trend. We can see if it's positive or negative. But we will discuss that more in the lecture where we're talking about correlation. So don't worry if you don't quite understand this one for now, but we call this a scatter plot. Sometimes they'll see it a scatter chart. Doesn't matter to me. And another bivariate, so this is a bivariate chart. It will always be a bivariate. Here's another bivariate. And the time series looks a lot like the scatter plot, in that we have two distinct variables. In this case, we got the year and the number of hurricanes that we had during that year is completely fictitious data. I just made up some data, so don't worry about whether or not this corresponded to reality or not. The difference is with a time series, you always have some aspect of time on the x-axis, sometimes called the abscissa, and then another variable on the y, but time will always be on the x-axis. And with a scatter plot, you don't connect the plots or the dots. You try to find one straight line that best fits your data. Call that the line of best fit. But with a time series, you actually connect the points. So how do we display a graph and in such a way that we can actually display real data without lying, but it also looks like we may have distorted reality a little bit. We sometimes do this unintentionally, sometimes it's done intentionally to fool the reader. And if you're not aware of it, sometimes it can catch you by surprise. So one way is to omit the baseline. In other words, you're not starting at 0 on the y-axis. There are reasons for not doing so, but most times when I see this, it doesn't seem necessary. It just seems there to distort the difference between two groups or multiple groups. Or you can do the opposite of this, is you can make your y-axis too big, so it actually flattens out the difference. And sometimes you just omit the label. So let me give you an example of each of these. So in this case, we did not start at 0 on the y-axis. We started it at 62. And so the actual difference in average height for men and women in the United States would be about 65 for women and maybe 69 or 70 for men. Again, I just made the data, made it up. So this is not wrong. But if you just look at it, it looks like men are substantially taller than women. In fact, twice as tall as women. So there are legitimate reasons not to start at 0, especially when small differences are important. But it's just important to keep in mind that it would look substantially different if we actually started at 0. So there's still a difference, a meaningful difference between the height of men and women on average, but this exaggerates that difference, in my opinion. So it's not a lie. There are legitimate reasons for doing this, but in this case, I don't think it would be a legitimate reason for doing this. Second way is you can actually do the opposite. You can distort this by making the y-axis too big. So in this case, since height, we have males with average of 6'9", or looks like 70 in this case, having a endpoint of 80 doesn't seem unreasonable. But what if I make the endpoint 140 inches? There aren't any people 140 inches tall. And so I've got all this empty space, and it actually flattens out the difference between my two groups. So if you want to exaggerate the difference between two groups, sometimes you can do that by not starting at 0. If you want to diminish the difference between two or multiple groups, sometimes you can make your y-axis just extraordinarily large, and it's going to flatten out that difference, even though the actual data is still accurately represented visually. It's a little misleading, in my opinion. And in this case, I don't know what this graph means. If you don't label your x and y axis, I don't know why you would do this. Maybe it's in the context of a situation where you're led to believe it's something positive or negative. In this case, it looked like, well, the libertarians are lagging behind, or whatever this happens to be. But we have no idea what it is. So because there's no label here, this is a meaningless graph. You can also distort, mislead the reader by manipulating the x-axis, sometimes called the abscissa. And we can do that by cherry picking the data. In other words, picking only part of the entire data set that best fits our narrative. or we can sometimes skip some data, especially on time series where we just delete some time, and we can use unequal scales. So here's my fictitious hurricanes by year, and over the long run, I don't see any nice trend that says it's going up or down. It just seems to be fairly random, holding still around 6 or 7 per year. But what if I decided to selectively choose these 4 years? Then it looks like there's a nice steady trend of hurricanes increasing year by year. So in this case, I have cherry picked this data set in order to get this graph. So with time series graphs, especially, to me, it makes a whole lot of sense to look at large scales of time to see what's going on. You can pick any couple of years where temperatures are increasing. You can find any couple of years where temperatures are decreasing. I want to see what it looks like over a long period of time. Second way you can do that is by just getting rid of some data. So again, we have another time series, and we got temperature by year, wouldn't fit over here. And in this case, it's completely fictitious, but we would have a gradual but steady increase in temperature by year, going up by tens. In this case, it looks like we have a sudden spike of temperature going up. The problem is, where's 1960 and 1970 and 1980 and 1990 and so forth? So I've deleted 60 years worth of data, and it gives me this illusion that there's been a sudden spike, where in fact we see it was increasing, but it was much more gradual. And then finally, sometimes we can make scales unequal. USA Today does this all the time. They love graphs. They make some nice graphs. I'm not picking on them. But the point is, whatever this is, and of course, this is a misleading graph because I didn't even tell you what this is. So we could say this is income, height, age, it doesn't matter. And I didn't even tell you what the x-axis is. So it's a bad graph. The point I'm trying to illustrate is whatever B is, it's 3 times the amount of A, whether that's good or bad. But because I've also distorted the width on the x-axis, looks like I'd probably fit maybe 10 of these guys inside this guy. So instead of just conveying the fact that B is 3 times the amount of A, it looks like B is 10 times the amount of A. And so there's no reason to do this other than maybe you're just looking clever. So let's look at some practice questions. The original data can be recreated from a histogram, and we know that's false. Original data can only be recreated from the stem and leaf, so that's false. Bar charts are often used with numerical data. We said bar charts along with Pareto and pi are often used with categorical data, not numerical data. So another false answer. A box plot or a box and whisker plot displays a 5-number summary, and that is true. That is the minimum, the maximum, Q1, Q2, and Q3. Occasionally, you'll get a 6-number summary with the mean being that 6th piece of data. It's acceptable to use unequal units on the x-axis. Like I said, that's false. That's one way to mislead the reader. A scatter plot is a useful way to display the interval frequency of a numerical variable. We said that's false. A scatter plot is a useful way to display the relationship between 2 distinct numerical variables. The interval frequency, that would be more of a histogram, would be the better answer. Time is always on the y-axis when using a time series. That's false. We know time has to be on the x-axis. When using a Pareto chart, the frequencies are arranged from highest to lowest. That is true. So a Pareto looks a lot like a bar, but one difference is from highest to lowest frequency, And the second one is typically you have that cumulative percent bar on top. A bar graph is displayed below, true or false. We said this is false. This looks like a histogram. So we have numerical data down here. So this is a histogram, not a bar. A frequency polygon. Is this a frequency polygon? It is not. This looks like a time series. So a frequency polygon is always going to be closed off. I put true, but this is actually false, so I need to correct this. This is not a frequency polygon. This is a time series. So this is the correct answer. This is not, sorry. What is wrong with the following graph? I have not labeled my y-axis, so I don't know what it is about Democrats, Republicans, and Libertarians that I'm trying to convey. What is wrong with the following graph? And this is where we've skipped all that data. So where is 1960, 70, 80, 90? So we're missing 60 years of data. It's giving the reader the illusion that we've got a sharp spike. What's wrong with this one? So this is one of those cases where we've got a lot of missing data, or we've got a lot of area that is just unnecessary. So I've made my y-axis too big. Logic would say maybe stop it at 75 or 80. So my y-axis is too large. Right. That's it for this one. As always, guys, you can call, text, email me 7 days a week.